question. So here we have a beam, overhanging beam, because AB and CD portion are overhanging at supports B and C. So there are two loads acting on this beam, one UDL and one point load at A. So first step will be, as explained earlier, the calculations of shear forces, the calculations of reactions. So I have calculated reactions here, so you can also calculate by using the equilibrium equations. So taking the moments at C is equal to 0, so the same sign convention I have used. So minus 200 into 8 plus VB into 7 at C point minus 180 into 10 into 3. Why 3? Because this whole UDL is acting at 5 meter from this in this beam, because this is whole 10 meter beam, so the UDL will act at 5 meter, and we have to find the distance between the point of application of this UDL and this C point. So this will be 5 minus 2, hence 3. So VB will be 1000, and using the equation sigma Fy is equal to 0, VC will also come out to be 1000. Now we will calculate the shear forces. So for calculation of shear force, I will move in this direction. So first I will take section here, then here, then here. So I have marked all the sections at different points. Okay, so first I will mark these 1, 2, 3, 4, 5, 6. Okay, so 1 is calculation of shear for the calculation of shear force at A. So this is the sign convention which we are adopting, positive and negative. So as in this left hand side, the downward forces are taken as negative, and this 200 is negative downward force, so there will be minus 200 Newton force at A. Then shear force at B, the second section, which is at just left of B. So here we will have two forces. One is this 200 Newton force, and another is this UDL acting in AB portion, which is of length, which is of value 180 Newton per meter, acting on 1 meter length. So minus 200, and again minus because this is downward, so minus 180 into 1. So minus 380 Newton is the shear force at B. Then for calculating shear force at B, just write, see the third section. So when I look at its back side, we have three forces, 200, 180 Newton per meter and 1000 Newton, which is the reaction. So minus 200 minus 180 into 1 and positive 1000, because upward force in left hand side are taken positive. So this is coming 620 kilonewton positive. To point C, so at C also I am taking two sections. So shear force at C on just left will be, so summation of all the forces on left hand side of section 4, 200, 1000 and this 180 Newton force acting on this whole length, right? So I will not take it together in whole length, because I have already taken one part, 180, which is acting on 1 meter. So I will write it this way. So I will start from A, so minus 200 minus 180 into 1 plus 1000. This we have already taken up to section B. Now another UDL is acting for 7 meter length, so minus 180 into 7. So we will get minus 640 Newton by calculation. Next is shear force at C, again on the right hand side, which is section number 5. So at this section, when we look at the back, we will get all the same forces, summation will be same, plus there is additional vertical force 1000 Newton. So I can directly write summation of all the previous forces is 640 minus 640. So minus 640 plus 1000 is equal to 360 Newton. Okay, this is also in Newton. I have written here Newton. And last is shear force at D. So shear force at D, I will take only one section because this is the end. So 360, all the forces up to point C are, summation of all the forces is positive 360. And another force which is acting is this UDL in this CD region acting for 2 meter length. So 180 into 2, and as we are looking on the left hand side of this sixth section, so downward force are taken negative. So 360 minus 180 into 2 we will get shear force as 0 Newton. Okay, so these are calculation of shear forces. Now the third step will be the calculation of bending moments. So I will first show the reactions. So for calculation of bending moment, we know that MA will be equal to MD equal to 0 because the endpoints of overhangs have 0 moments always. Okay, bending moment at B will be, so again sign convention I am mentioning here so that you don't have any confusion. So the bending moment at B, if I take section and just left of B, will be 200 into 1, which will be anti-clockwise, and anti-clockwise on left hand side are taken negative, right? Minus 180 into 1, which is another force acting here, UDL, and it is acting at a distance of half, 1 by 2 from B, half from B. So we will get minus 290 Newton. We will calculate either from this direction or this direction. So when I am calculating in this direction, I will have to take all the forces, that is 200 into 8, minus 200 into 8 plus 1000 into 7, and minus this whole force 180 Newton per meter up to point C. So instead of that, I will move from this side. Okay, so I will mark a section at just right. Okay, you can do it anyway. For easier calculations, I am taking a section at just right, and here I had taken section at just left for B. Okay, so when I'm taking section at just right, so of this C, so I will look on right hand side of this section now, and here I will have only one force, so the calculations will be easier. So the only one force here is the 180 Newton per meter force acting on 2 meter length, and it will provide a moment of 180 into 2 into 2 by 2, which is 1 meter, and it will be clockwise. So on the right hand side, now as we are looking on the right hand side, so see, on the right hand side, if the moment is clockwise, then it is taken negative, right? Moment will be like this, so it will be clockwise, and we are looking at the right hand side of the beam, so it will be negative. So minus 360 Newton meter, right? So these are all the moments for now which we can calculate. Now we will move to plotting the shear force and bending moment diagram for this. So bending moment at A, okay, so first we will draw the shear force diagram. So shear force at A was minus 200. So I will plot it here, 200 minus. Then shear force at B was minus 380. And at B also we had taken two sections, at left and at right. So at left we had minus 380 and at right part of the section the value was 620. Then at the left side of C we got the value as minus 640, so downward side. Then on the right side of C the value was 360 and at D the value was 0. Okay, now we start joining them from this to this direction. So at A 200, and as there is UDL we will join these two with the help of inclined line. Then the shear force changed from 380 to 620. Then from 620 is dropped to 640, and again due to UDL we will join these with inclined line, then vertical line, because it moved from minus 640 to 360, and then 0. So this is the shear force diagram. Right now, for the bending moment diagram, here at A and D we have 0 value. At B the value was minus 290, and at C it was 360. Okay, so as we have UDL, so we will join these with a parabolic curved line, right, like this. uh, my bending moment diagram is incomplete because we have plotted these four values 0, 0, 2, minus 290 and minus 360, but we have yet to cover this part, and in this part we are not sure where we will get the maximum bending moment. Okay, we are from the basics we know that there will be bending moment somewhere between, maximum bending moment somewhere between B and C, but where will be that we cannot say for now, that exactly at which point will that be maximum. So for this you must know this concept, that bending moment is maximum where the shear force is 0. Right, this is the best method to locate the bending moment. Right, so here in this case we have already drawn the shear force diagram, so we know that where the shear force is 0. So we can say that at this point, which I am extending like this, so at this point shear force is 0. So this means when I look at my beam, if I call this now point E, the shear force will be 0. Right, but we don't know for sure up till now that where will this be located in the beam. So let me call this distance x. So first to calculate, first of all, so we want to calculate the maximum bending moment. So to calculate the maximum bending moment, we have to first identify the point of 0 shear force, because at the same point we will have the maximum bending moment. Right, so for that I have taken the distance to be x of this point E, where we will have maximum bending moment. Right, maximum bending moment. So if this is x, this will also be x in the shear force diagram, and this will be 7 minus x. Okay, so the fourth step in this question will be calculation of maximum bending moment. So when we are calculating maximum bending moment, first locate the point of maximum bending moment, which will be the point of 0 shear force. right? So I will draw the diagram again here. So in this beam, this beam we are having, right? So we have calculated we have plotted the shear force diagram, something like this, right? In this middle portion BC. So this value is plus 620, this is minus 640, right? So and this is x, this is 7 minus x. So this we are locating the point E. So using similar triangles theorem, the ratio of the sides of these triangles must be same. So x upon 620 must be equal to 7 minus x upon 640, right? So therefore x is coming out to be 3.44 meter, and this distance is from point B, right? So this we have now calculated 3.44 meter. So we can say that bending moment will be maximum at a point E having a distance 3.44 meter from B. Okay, so now I have located the point. Now I just need to find the bending moment at this point E using the same concept which we did while calculating other bending moments. Just point B. So so I want to calculate bending moment at E, right? So I will take a section here, right? And then take the summation of all the moments on the left side of this section. So that will be 200 into 4.44 and negative sign, because in the left hand side the negative anti-clockwise movement are taken as negative and clockwise are taken positive. So this will have anti-clockwise movement. So minus 200 into 4.44, 1 plus 3.44, right? Plus 1000 into 3.44. Moment due to this reaction on this point will be clockwise. And this UDL will be also have anti-clockwise. So 180 into 4.44 into 4.44 divided by 2. This will be the moment due to this UDL on point E. So after solving this, we are getting the maximum bending moment at E as Newton meter, right? So this is the maximum bending moment. So now we can easily plot it, and it is coming positive. Okay, not negative, it is positive. So again we will go back to our bending moment diagram, and now we know the location of this x. So this x we can write as 3.44, right? Okay, this we know at 3.44 the shear force is 0, or the bending moment is maximum. And so at this point 777.78 Newton meter positive. And again this is a UDL, so we will join these with a parabolic curve. So this is the bending moment diagram of this type of beam.